Yeah, so the topic on simple regression analysis is the foundation of what we know as regression analysis. And of course, this is just the starting point. Regression analysis could get very, very, very complex and very, very verbose in terms of the strategy, the technique, the data that is used, and all that. And it depends on several factors. What is the dependent variable looking like? Is the dependent variable a quantitative or a qualitative variable? Is the data a time series or a cross-sectional data? Do you have, is it a panel data? Panel means you have data that varies across both time series and cross-sectional. So, but without going too deep into all of that, for us, the level of this course just needs that we introduce you to regression analysis. So, the basics of regression analysis is simply to establish causal relationships between variables. And when we establish causal relationship between variables, the aim is to be able to determine how we can influence one variable by changing or tweaking another variable. So, for instance, if we want to improve GDP, how do we improve GDP? You need to know the factors that affect GDP. If we know the factors that affect GDP, and we are able to say that if you increase or reduce those factors based on whether they are significant in affecting GDP, then we are sure that we would affect GDP, right? Let's take, for example, that government wants to reduce poverty, let's say by 20%. And government knows that based on a regression analysis, government has been able to establish that if you increase grants to SMEs by 20,000 per SME, poverty will reduce by 10%, for example. So what that means is that the government just needs to increase grants to SMEs by 40,000 so that poverty will reduce by 20%, because 20,000 will reduce poverty by 10%, and then 40,000 will reduce poverty by 20%. So to attain the goal of reduction in poverty by 20%, the government needs to know the extent to which it should increase grants to SMEs to be able to know how to achieve that goal. And that is where regression analysis comes in. Because with regression analysis, there is need to establish a clear relationship between the variables. And these variables, you will hear me talking about the dependent and the independent variable, or what we call the response variable and the predictor. So response variable is the same as dependent variable, and independent variables are the same as predictors. So, and it's important for you to understand that relationship. So in the example that I've just given, grants to SMEs is the independent variable or predictor. Poverty is the dependent variable or response variable. So when I say the impact of X on Y, Y is a dependent variable because you're saying on Y. I think we talked around this in the first lecture. So the relationship is causal. If the relationship is causal, then we are able to know that if you affect one, or if you change one, you'll be changing the other. But if it's not causal, then a change in one will not necessarily change the other. But that is the background behind regression analysis. Now, the most simple form of a regression analysis is where we have just two variables, one independent variable and one dependent variable. regression analysis could have many more independent variables. It could have many more independent and dependent variables, and it gets more and more interesting. We'll talk about simultaneous equations, matrices, even the computational general equilibrium models, and so on. But in its most basic form, regression analysis is simply the dependent variable and the independent variable, one independent variable. And it's important to note that for a functional form that just has one dependent variable and one independent variable, that could only be visible in a theoretical framework, because there's no variable that is affected by only one thing. So before you finish listing the things that affect a particular variable, then you would have listed all the independent variables that affect that dependent variable. So you need to determine the equation that you are working with based on the factors that you have determined to affect the dependent or the independent variables. And we can see this in a scattergram. So when we look at a scattergram, here we are simply showing the relationship between x and y. Now, the dashed lines come in later. What we normally have initially are these stars, the x's in the graph, which simply represents each observation. So the lowest x, for example, could be 10x and 10y. So 10x, 10y will give us the lowest x, the lowest points here. And then maybe another observation, 20y and 10x is the one up, and so forth. So when you have plotted the information from x and the information from y, and you draw a line across the informations, across the dots or across the observations, and you have this kind of straight line where we say the line follows a 45-degree line pattern, then we say that this relationship is linear. The relationship between x and y is linear. But if you finish plotting the observations for x and y, and the curve that you have is going in this direction, it simply means it's exponential, which means the rate at which x changes y is not uniform across, because when x is low, a unit increase in x will only affect y slightly. But as it goes up, you see that the relationship, the slope changes. So, and this complicates the relationship. But for now, we are only interested in linear relationships. So with the advantage with a linear relationship is that once you have a linear relationship, you can say without fear or favor that a unit increase in x increases y by this certain amount, which means as long as x keeps increasing, y keeps increasing. And that's not always the case, and I think I've given you an example of that in this class. Let's take another one. Imagine that the relationship between rainfall and yield of maize is not linear, because as rainfall increases, let's say rainfall is our x, as rainfall increases, the yield of maize increases up to a certain point. Beyond that point, increase in rainfall will now become a problem to maize. That's why floods affect maize negatively, because you have a lot of water, but the water is now not longer good for the crops. So with agricultural functional relationships like the relationship between rainfall and maize, the relationship is not linear, because it's not true that for every rainfall that increases, for every increase in rainfall, yield in maize will increase. At some point, yes, it's good at the beginning when there's no rain. When there is drought, you need rain. So every drop of rain will improve maize. But as rain continues to fall, it becomes a problem at some point, such that increase in rainfall will negatively affect yield maize. So you have a quadratic equation in that case. That's the most clear example. But this is an exponential relationship, which is also not a linear relationship. For a linear relationship, you have something like increase in what good example, perfect example can I use, or near perfect? There's nothing like perfect, especially when it comes to regression analysis. But let's say the increase in um, income will reduce poverty, right? Increase in income is expected to reduce poverty. If it's not reducing poverty, then other factors like maybe the distribution mechanism and all that are affecting that. But the expected relationship between income and poverty is a very direct one, that the increase in income should reduce poverty. So in that case, it's still linear because there's that inverse relationship, but it will now be negative. It will not be a non-linear relationship. It will still be linear because for every increase in income, poverty reduces. Yeah. So there's no point in which we will be saying above this income level, poverty is not reducing again. That's the general theoretical expectation. But for the purposes of this class, we'll be using only the linear relationship examples. Any question up to this point? No questions? Okay. So now let's get into the nitty-gritty of a regression. Maybe I should start with a practical example. If I were to ask, now I need you to unmute and talk. If I were to ask us, what are the factors that affect performance in class? What will be those factors? Anybody?
Prof, let me try attendance.
Yeah, good. Attendance of lectures, that's one. Any other person? Performance is a function of attendance. Any other person? Is it also a function of answering question in class?
Maybe lack of understanding.
Lack of understanding is an ambiguous
That
one. Let's say, let's qualify the lack of understanding. Should we say either poor teaching methods or inexperienced teachers? Yeah, we could take one of that. Because lack of understanding could be caused by several other factors. That's right. Yeah. Any other
Access to
person?
study materials.
Yes, access to study materials. That's a good one.
Readiness or preparedness, like maybe students that don't prepare
Okay.
for assessment.
Okay. Preparedness of students. Now, let's work with this one. So you have given 4 factors that affects performance. Now, so if we were to establish the factors that affect performance, or if we were to look at the extent to which being prepared in school affects performance, let me even take that second one because it's more direct. So if we're interested in seeing the extent to which a student's preparedness affects performance in class, the first thing that you should note is that performance will be your Y variable. Performance will be the dependent variable because what we are looking at the factors that affect performance. So the factors on performance. So performance is the dependent variable, or what we have called the response variable. Then all the factors that we have mentioned, preparedness of students, access to study materials, inexperienced teachers, attendance, all of that will constitute independent variables or predictor variables. Now, these independent variables are all factors or key factors that affect performance, which means that even if we are interested only in how preparedness affects performance, we must pay attention to, we must include these core variables that affect performance, because these core variables are also key factors of performance. And why we need to do that is because when you do that, you are able to isolate the unique impact of preparedness alone. Because if you just run a regression, which is why I said a simple regression model with just one independent variable is only a theoretical concept. Because in reality, if we just estimate preparedness, yes, the record, we'll be having a record. So if we just use preparedness as the only independent variable, it means that information from the other factors that we have listed, being attendance, experience of the teacher, access to students, and so on, will be clumped, will be masked into preparedness, such that when we see the relationship between preparedness and performance, we will not be having a valid coefficient, we will not be having a valid figure for that relationship. So for us to have a valid figure, we need to include these variables. And you will see that when you get to start doing your thesis. But for the purposes of this topic, I will see that also when we do the practicals. But so the other thing I should mention is that we have listed 4 factors that affect performance. So performance is a function of attendance, it's a function of experience of teachers, it's a function of access to study materials, it's a function of preparedness of students, right? But there are several other factors. We could have list up to 20 things here, right? But regression analysis is conscious of that. It's conscious of the fact that there will be core factors and there will be those many other things that are not really important, but that in a way they may affect the dependent variable. We can list them. I can say, for example, marital status of students. Yeah? Marital status of students, social life of students, whether the student lives in a house that has power or not, if there's anything like that. So my point is, I can list so many small things. Number of children of students, whether the husband beats the wife. You see, that list can be endless. So once you have put together all the factors the core factors that affect performance, all these other small factors are summed up in what we call the error term. So if you're looking at your screen, the error term is that last E, which is the error term. So like we have said, we are doing only a bi-directional or what do we call it? Now I'm forgetting this. So we're dealing with a simple regression. A simple linear regression means just one independent variable. A multiple linear regression means many independent variables. So let's assume that we are dealing only with performance, which is Y, and preparedness of students, which is X. Then all other factors will be summed up in the error term. And so the error term caters for all the omitted variables. It caters for any mistakes that have been made between that relationship. The error term is all-compassing. Now, why do we have an error term? Because we have an error term in economics because we are dealing with human beings. We are dealing with social beings. And because the relationship between human beings are not exact, you must account for a margin of error, right? When the scientist says oxygen carbon dioxide is 1 carbon and 2 oxygen. That is the same everywhere in the world. Wherever you go to, if you take 1 carbon and 2 units of oxide and you put them together, you have carbon dioxide. That is true everywhere. But with social sciences, it's not always true what we see with relationships. An increase in income for uni may mean an increase in leisure time. An increase in income for another person may mean an increase in investments. An increase in income for a third person may mean an increase in number of cars, whatever. So because human beings are not predictable, and because it's difficult to encompass all the variables that affect a particular dependent variable, the error term is meant to cater for all these differences. But the point of the regression is to be able to minimize these errors and bring the observations as close as possible to the linear trend. And we'll see how that linear trend works. So when we minimize the error, which is this E, when we minimize the error, we now have, so what we have in the second equation, y hat equals a plus bx, is now the estimated equation. So when we estimate a regression, what we have is a plus bx, which means we have been able to minimize the error term. Now, when we minimize the error term, we can safely say that a unit increase in x increases y by the value b. So b is the coefficient of x, and a is the intercept. Intercept is more or less like the starting point. So the intercept is the starting point, which is always a constant. It's not a big deal. The big deal for us is the b, which is the coefficient, because it explains the extent to which we can increase y, and we would have practical examples to see how that works. So if we have observations that are scattered, like what we have here, like the example I was using. So x1, y1, like on this graph, can be put, you can establish where x1 and y1 lies on this graph, which is the x just close to E1, and maybe x2, y2, x3, y1, x2, y2, and so on and so forth. So we have all these observations, and let me go to a table just to show you. So it's something like this. So you can draw a graph for temperature and length. So that when you draw the graph, you have a 13, you have a 5, you have a 20, you have a 5.5, you have a 29. So each pair of observations will give you a particular dot on this graph. So when we do a regression, we have what we call a line of best fit, which graphically is simply a line that goes through all these observations. And when the line goes through all these observations and is showing like this 45-degree line pattern, then it means that there's a linear relationship between x and y. And it's safe to say that as x increases, y increases. Always. So there's a continuous relationship, continuous positive relationship between x and y, such that as x increases, y keeps increasing. That's why we have this linear relationship. Now, remember what we said about y hats and a plus bx. So the regression, that the OLS, for example, which is the most popular form of doing the regression, the simple linear regression, what the OLS does is that it gets, of course, you have values for y and you have values for x, which is like in the table that I've shown you. So when you run a regression, having values for y and having values for x, it produces the value for a, which is the intercept, and produces the value for b, which is the coefficient. And then you will not see the value for the error term, but you can generate it. You can actually generate the error term from this relationship. But your estimated equation will simply be y hat equals a plus bx. Now, what that means is that you have minimized the observations that are far away from the linear trend, such that you can interpret the relationship based on just this linear trend. And this linear trend has observations for A and for B. But now we want to see how we can compute that relationship between how we can compute A and how we can compute B. And to do that, we use the principle of linear squares method. And like I've said, there's a procedure to develop or prove that we can minimize the sum of squares of residual such that we eliminate the error term. It's a long proof. It's beyond the scope of this course, so we will not be going detailing into all of that. But we can see the formulas for computing A, which is the intercept, and the formula for computing B. So these equations are given from the method of least squares, this one and this one. Summation y is equal to na plus b summation x, and summation xy is equal to a summation x plus b summation x squared. These two are proofs. So when you have this, you prove it's a long proof. When we used to solve it, it takes 1 or 2 pages to prove that a is equal to summation y minus b summation x over n, and b is equal to n summation xy minus summation xy summation x summation y all over n summation x squared minus summation x all squared. Now, these values, I believe, you can compute them even based on what we did in the last lecture. So if you have a table, before I go to the next slide, so if you have a table that has y and that has x, to solve for a, you just sum y, you get the value and put here. B, you have it when you have solved for b, so you must start with b before you come to a. Summation x is the sum of the values for x. N is simply the number of observations. So summation y, b, summation x, and n, if you have that, you can compute a, which is the intercept. And then if you have, then for b, that's where you need to do, maybe put up another column where you multiply x and y and then sum them. And then you take again the sum of x and sum of y that you have already used up here. And you also square the value for x, square the value for summation of x, and then you have everything that you need to compute for b. So if we look at this graph, you would see that what a and b are. A is the starting point of this linear trend, which means a will be somewhere under y1 hat. I don't know if you can see my cursor. A will be somewhere here under y1 hat. That's where this line of best fit starts. So that's where the intercept is always. A is always that. And then B is the slope of this line. So any point on the line, because it's a straight line, to take the gradient of that line is to know the value for B. So if we take the gradient of this line, it's unfortunate I can't write on the screen to show you exactly what I'm saying. And if I leave the screen to show you on Paint, I may lose the recording. So, but yeah, the slope, if you understand what the slope is, then you understand what I'm talking about. The slope of this line is simply the value of B, and the starting point of the line is the value of A. Now, a more practical way to look at it is to look at the table, which will give us a much clearer picture. But before we get to the table, any questions? Remember, you should stop me if you're not following. I know this class is a notch higher, and I know some of us do not have economics background, so I'm not assuming anything. I'm just explaining, and if you feel I'm fast, please stop me and ask your questions. Okay, I'm assuming that we are all good. Okay, if you're following, can I see your hand? Okay, 3, 4, 5. Okay, okay, okay. So good. Okay, that's nice. So now this is a practical table where we have temperature and length. Now, so the example is saying using the data from a rod heating experiment as shown below, estimate the line of best fits using OLS. Rod heating experiment. You know what happens when we heat rods, right? When you heat a rod, the length increases. When you heat it, it increases. So that's how knives are made. Original knives are very short, or swords. Swords may be very short, but as you heat it, you can keep extending it, and it becomes longer and longer and longer. With increase in temperature, it can melt a little, and then you can have a longer and longer rod, right? So what this table is saying is that when the temperature is 13 degrees Celsius, the length can go up to 5.10. When temperature increases to 20, the length goes up to 5.25. When the temperature increases to 29, the length goes up to 5.46, and so on and so forth. When the temperature is 78, the length would have moved from 5.10 to 5.98, which makes it the longest period, right? Now, from this table, we can compute our A, which is the intercept. We can compute our B, which is the coefficient. Now, when we compute A, we know the formula for A, but because the formula for A has B in it, we will not start with computing A. So to compute B, the first term here says N. Now, our N is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 observations. So our N is equal to 10. The next item here is summation xy. How do we get summation xy? We multiply x times y and sum it all. So the best way to do this, you get another row, maybe below length, and then you say 13 times 5.10, you get the value. 20 times 5.25, you get the value. 29 times 5.46, you get the value, and then you sum all of them such that you get summation xy. The next term, you have a minus, and then you have summation x. Summation x is simple. You just need to sum all the values for temperature. 13 plus 20 plus 29 plus 39, and so on and so forth. You sum y, you get all the values for length. 5.10 plus 5.25 plus 5.46, right up to 5.98. The denominator, you have another n, which we have established to be 10. Then another term we need to solve is x squared. So what is x squared? X squared is 13 squared is sum of x squared, right? Sum of x squared, 13 squared plus 20 squared plus 29 squared plus 39 squared right down to 78 squared. You get the value for that, you have your sum of x squared. And take note that sum of x squared is different from sum of x all squared. So sum of x squared is what I've just explained. The sum of x all squared is just taking 13 plus 20 plus 29 right down to plus 78. You sum it and then you square it. So once you do that, you have all these values that we have here. Summation x is equal to 467. Summation x squared is 25717. Summation xy is 2674.93, and so on and so forth. So you can do all of this and get all the answers. And please take your precious time to do this step by step and get all these answers and confirm that they are correct. and because you are expected to know it, right? Based on the formulas. So when we do that, we can substitute in the formula for B as we have seen, and then B gives us 0.013. A, when we have the value for B, which is 0.013, we can substitute in the formula for A, given the other values for summation Y and summation X, to have 5.011. So it means that our Y hat is 5.011, which is A, which we have computed, plus 0.013, which is the value for B, X. So, and we know that X is temperature. Y is length. How do we know? We know because we have said this is a rod heating experiment. And we know that the temperature is heating the rod to influence the length. So remember I've said what the factor is the independent variable. What you're investigating on is the dependent variable. So because you're looking at the effect of temperature on length, then length is your dependent variable, which is Y, and temperature is your independent variable, which is X. Now, how do we interpret? This is very important now. How we interpret this, I guess you should write this. I didn't state this clearly, very clearly in this. Of course, I've explained this. Yeah. So how we interpret this, all things being equal, a unit increase in X, which is temperature, all things being equal, a unit increase in temperature increases the length of the rod by 5.011 centimeter. And in this case, we even know the units, so we don't even need to say a unit increase. So we can say all things being equal, a degree Celsius increase in temperature increases the length in centimeters by 0.013. And we are saying increases, we are using increases intentionally because what we have in front of 0.013 is a plus. If it were a negative, we would say a unit increase in temperature reduces the length of the rod by 0.013. We are saying increases because we have a positive there. Is that clear? This is written here. In other words, for every rise of 1 degree Celsius, the length of the rod increases by 0.013 centimeters. And we can only say this in this way because there's a linear relationship between temperature and length. For every increase, if there's not a linear relationship, we will not say for every increase. But we can say for every increase because there's a linear relationship. As temperature increases, the length of the rod increases. Any questions? I expect questions now. Especially for those who are seeing this for the first time. Are we good with this? Can we all do this?
So I just wanted maybe for you to explain to us the catch, because for some reason I am still mixing up the Y and the X axes. It's like I'm switching the two. So like, what is the catch? How can you identify it?
That's a very important question because once you mix that, imagine mixing that here. It means when you're summing for Y, you should rather be summing for X. So it's important to know the relationship. And I said the best way to know the relationship is to know which factor is affecting which one. The variable that is affecting the other one is the independent variable, is the X. So if we say, how does preparedness affects performance? Preparedness is your X. what is being affected is the dependent variable. Now, even from the names, dependent means the variable is depending on a factor. So dependent means the variable is depending on a factor. So if we say, how does preparedness affect performance? Then we are saying performance depends on preparedness, right? And why it becomes a bit tricky is because the relationship will not always be causal. There are some relationships that will not always be unicausal. There are some relationships that are bicausal. So it's in the context of the question that you determine which one is the dependent and which one is the independent. So if the question, for example, says, how does income affect education? It means that in that question, education depends on income, right? How does personal income affect education? That question says that education is your Y, the dependent variable, and income is your X, the independent variable. And we know that we can flip this relationship to say, how does education affect income? So the moment you switch it and say, how does education affect income, it means you're saying income depends on education, which means income is your dependent variable, Y, and education is now your independent variable, X. I don't know if I've confused you more or made things better.
No, thank you, sir. I think with more reviews, it will settle in.
Okay.
But it makes sense.
Okay. Any other questions? Especially the interpretation. So when interpreting the coefficients, there are three things that we normally look out for. The third one is not here yet. We'll see the third one in due course. But the first and the second are here. The first one is, so the three of them is the three S's. The first one is the size of the coefficient. In this case, it is 0.013. The second is the sign of the coefficient. In this case, is the plus. The third is the significance of the coefficient. To interpret the significance, you need either the probability value or the t value. Now, the probability value, when the probability value is less than 0.05, we say that that variable is significant. But with the information we have right now, we have not been given the probability value, we have not been given the t value. So we'll get to that. But when you listen to my interpretation, you can see, okay, you can hear very clearly the first two S's, the size and the sign. When I say all things being equal, a unit increase or a temperature increase in by 1 degree Celsius will increase, that's the first S. Increase is the sign. Will increase the length in centimeters by 0.013, the second S, which is the coefficient. And you factor the two. Now, the intercept, which is 5.011, I've said is of lesser importance because it simply tells us where the graph starts. But it also tells us the value of y if x is 0, which means if for any reason x is 0, it means that the length is simply equal to 5.011, which means if there's no heating, to take the context of this question, if there's no heating at all, then the length of the rod will simply be 5.011. Once you start heating, the length now changes with the change of the coefficient, which means the extent to which the temperature changes will now change the length of the overall length of the rod. I hope that is clear. So, the ultimate aim of regression is not just the beauty of saying a unit increase in this increases that. Beyond that, we use this regression line to do what we call interpolation and extrapolation. Now, interpolation is when we try to predict variables within the model or within the data span that we have. Extrapolation is when we try to forecast beyond the data points that we have. If we look at this table, our y, for example, varies from 13 to 78. If I want to get the value of, let's say, 29 or let's say 25, even this 25 that is in between 20 and 29. So this is still interpolation because the value falls between 13 and 78. But once I want to get the value when temperature is 120, for example, then that will be extrapolation because 120 goes far beyond the maximum value of our sample, which is 78, temperature of 78. So interpolation and extrapolation is very important, and forecasting is more tricky than interpolation. When we extrapolate, it's more tricky than when we interpolate. It's much more risky because, and that's why the central banks and other institutions use very robust methodologies to extrapolate because, as we'll see, there are issues with just using the OLS to extrapolate. So when we hear the central bank, for example, saying that GDP in 2030 will be a GDP growth of 13% in 2030, is because they have been able to do simulations and they've been able to know that this is how investment will affect GDP, this is how inflation will affect GDP, this is how exchange rate will affect GDP, this is how you understand. So when they put all that together in the simulation model and they say, okay, if we make investment to be this and this and this and this for the remaining years up until 2030, if we make sure that inflation is this, if we make sure that exchange rate is this, if we make sure that all the other factors are respected, then we are sure that in 2030, GDP will be this amount. That's extrapolation. So, but to give you a sense of both interpolation and extrapolation, we can do that by simply substituting values into our regression that we have estimated. So we have computed the values for A and we have computed the values for B. And so we have the value for A, which is 5.011. We have the value for B, which is 0.013. And then we have the value we want to extrapolate. So we are assuming that, for example, temperature is 50 degrees Celsius. Remember, we have said X is temperature. So if we say temperature is 50 degrees Celsius, and we substitute X with 50, then the answer will be 5.011 plus 0.013 times 50, which will give us 5.66 centimeters. Now, what this means, what this equation means, is simply saying that if we heat the rod to 50 degrees Celsius, then the length of the rod will become 5.66 centimeters. Now, of course, this is an OLS estimation result. What we have in reality is the value is 5.68. In the table that we have, under 50, what we have is 5.68. But according to our OLS estimation, it is 5.66. So there's a difference of 0.02. Now, that difference is negligible because if we round up, for example, to 5.7, it will be the same thing. But the bigger point is that the OLS estimate brings us as close as possible to the answer when we do an interpolation. And so with this regression result, I don't even need the sample. I just need to know where the sample starts and where the sample ends. And I can determine any value within that sample based on this regression result for A and for B. And we'll come as close as possible to the real or the observed variable or the observed data. Now, let's consider a case of extrapolation. Extrapolation, like I've said, is going beyond the scope of the sample that we have used. When we go beyond that scope, if the scope in this case ends at 78, if we look at the table, temperature, the highest temperature is 78, which means anything from 80 and above, or from 79 and above, is beyond the scope. So let's try 80. When we try 80, what we see is that when we substitute 80 in this regression results, we have 5.011 plus 0.013 times 80, and it gives us 6.05 centimeters. And you would see that this is as close as possible to what we would get if we had an 80. Not because it is within the sample, but because 80 is still not too far from the maximum value of x, which is 78 degrees. So there's just a difference of 2. But if we follow the same extrapolation and maybe assume that temperature increases to 1 million degrees Celsius, when temperature increases to 1 million degrees Celsius, if you substitute 1 million in our regression, such that we have 5.011 plus 0.013 times 1 million, then the value you would have will be 130.18. Now, while that looks like is true or is valid, it's not true, especially with this example, because we know that once temperature goes to 1 million degrees Celsius, the rod will melt. There will be no rod, right? You don't even need to get to 1 million. Once you get to 100, 200 degrees Celsius, the rod is already, that's boiling point and melting point coming up. So you see that extrapolation can be very tricky and may not be valid, especially the further you go away from the maximum value or away from the sample size, the minimum and the maximum the values of the sample. Is that clear? Can I see your hand if you're following? Okay, I'm happy. Okay.
Sir,
Yes.
can I ask something?
Yes, please.
Say in your research, where do you make use of this regression analysis?
We
At what
always
stage?
do that. I do that almost on a weekly basis. So when you're doing your research, for example, let's take a practical example. Do you have a topic?
Let's use the what? Financial inclusion.
What relationship do you want to look about with financial inclusion? Are you looking at what financial inclusion?
Maybe the impact of financial inclusion on women, for example.
On women, let's say on women growth, or let's say financial inclusion on the empowerment of women.
Yes, yes.
Then that will mean that we need to qualify empowerment of women. If we qualify empowerment of women to be the amount of money in their bank account, then, or their ability to have assets, or their ability to basically take decisions, financial decisions. So I'm just trying to say that that empowerment can be a bit ambiguous and that you need to qualify it. But let's just say money in bank account. So what is financial inclusion? Financial inclusion is also a very broad term, right? But let's just take one aspect of it, which is having a bank account. So if we proxy financial inclusion with having a bank account, then invariably it means that it could affect the ability of women to have money in their bank accounts. Because if you don't have a bank account, you can't even talk about having money in the first place. And also there are other issues with that relationship, econometric issues. But for the sake of this example, let me just use what we have. So if you're looking at the impact of financial inclusion on empowerment of women, then empowerment of women will be your Y, and financial inclusion will be your X. And we have said for the example that the relationship between X and Y cannot just be that simple, that you need to take into consideration other factors that affect empowerment of women. Now, when you take your financial inclusion, which is having a bank account, those will be, so it means that your variable would be a qualitative variable, because having a bank account is either yes or no, which means you would say if having a bank account is yes, let it be equal to 1. If having a bank account is no, let it be equal to 0. Maybe not the perfect example now, because that will mean we are doing a qualitative response models, which you can't use an OLS to do, because the dependent variable, which is the dependent variable is empowerment of women, and the independent variable is having a bank account. But for the sake of computing A and B, we need both quantitative variables. So let me think of another thing. Maybe, a good example. Students' grants, which is close to the financial inclusion stuff. Student grants and their performance in class. Let's assume that they get different amounts of grants, right? So it means that, and the grant is with respect to their performance. So let's say for a student that has, if we do a survey and we are going around and asking, how much grants did you get? A student says, student A says, I got 3,000. What was your performance? My CGPA was 4.1. Another student says, I got 2,000. My performance was 2.1 CGPA. Another one says, I got 5,000. My performance was 3.2 CGPA. Another one says, I'm sure you get the point now. So it means that you have something very similar to that table that we have, which is student grants, and you have varying amounts for that grant, and performance, CGPA, which you have several CGPAs. And so you can use those two to compute your A and your B, knowing that if we are saying the impact of student grants on student performance, then student performance will be your dependent variable. And then student grants will be your independent variable, your X. So when you're summing X, you would sum student grants. When you're summing Y, you will sum performance. And then you will still boil down to the value of A and the value of B. And the value that you get for B, you can interpret that regression estimation result as a unit increase in student grants increases performance of student, as if it's positive, by the value B. Is that clear now?
Yes, sir. Thank you.
Okay. Any other question? Okay. So now going to example 2, we have a question here, a similar question like we have seen. The example here is saying a large field of maize was divided into 6 plots of equal area, and each plot fertilized with a different concentration of fertilizer. The yield of maize from each plot is shown below, right? So we have concentrations of fertilizers measured in, how do we call this? Ohs meter square, not too sure. And then we have yield, which is measured in tons. So for a concentration of 0, fertilizer concentration of 0, when no fertilizer is applied at all, we have 15 tons produced. Then when we have 1 unit of fertilizer applied, the tons increase to 22. When it's 2, the tons increase to 31, right up to 5, and then it increases to 54. So the first one says, obtain the equation of the regression line for yield on concentration, giving the values of the coefficients to 2 decimal places. So this question is basically asking you to look for the value of A and to look for the value of B. Once you have the value for A and B, you can establish that relationship of the y hat. Y hat equals A plus bx. So you just replace A and B with the values for A and B that you have gotten. 2. Interpret the regression coefficient in the context of the problem, which is simply what we have seen, what we have talked about. So when you're interpreting, you will say all things being equal, a unit increase in fertilizer concentration by Ohs meter square will increase or decrease based on what you see with the sign, will increase the tons, the use of maize in tons by the value of B. That's what is expected in point number B. 3. Use the regression line to obtain the yield when the concentration is 3 Ohs meter square, and state precisely what is being estimated by this value. So when you substitute now 3 in your regression line, then you can get the answer for question C. And of course, state precisely is simply saying we have 3 units of concentration, fertilizer concentration. When we have 3 units of fertilizer concentration, the value of the yield in tons is equal to, let's say, 40.5, if that's the answer. And just to explain further, 40.5 is not exactly 40, but it's approximately close to 40. D, state any reservations you would have about making an estimate from the regression equation of the expected yield per plot if we had 7 Ohs per meter square of fertilizer. So it's talking about extrapolation. How do you interpret extrapolation? Of course, you must first compute use 7 as the concentration value for fertilizer in your regression that you have computed, get the answer, and then speak to what that means for extrapolation. Now, you should also be very careful because you know that fertilizer, in this particular context, fertilizer beyond a certain point may not be linear. That is why it's also important when you talk about extrapolation. If you say concentration of 15, then you may now be choking the plants, which may not necessarily be increasing yields, but may be reducing yields. So keeping a short a range of fertilizer from between 0 and 5 is to allow a sample that will have a linear relationship. Beyond that, the relationship may not be linear, but 7 is close enough. So all what I've explained, it means that your answers for B, C, and D are largely dependent on your answer for A, which means once you fail A, God forbid, it's likely to affect B, C, and D. But the answers for example 2 are all here. And just to give you a snippet of what is expected, but like I said, when doing your reviews and your revisions, please do not hurry to get to this page. When you are here, try to answer all the questions, and then you can move to the next page to confirm your answers and to confirm that these answers are correct. Anyone that is not correct, please call my attention to it so that we correct it as soon as possible. And then we have example 3, which is basically the same thing. A company monitored the number of days of business trips taken by executives of the company and the corresponding claims they submitted to cover the total expenditure of these trips. A random sample of 10 trips gave the following results. So when one executive took 10 days, it costed 116 euro. When another one took 3 days, it costed 39 euro. When another one took 8 days, it costed 85 euro, and so on and so forth. The same analogy. You look for A, you look for B, you get a regression line, you interpret it, you interpolate and extrapolate, and then you get the answers on the last page. I wanted to just give you the questions just like that, but giving you an idea of the answers, I think, will also help. You just need to still discipline yourself to make efforts to solve this actually before looking at the answers. Any other questions? Who is happy with this lecture? Who understands it very well? Nobody?
Prof, I can personally only say I understand it well if I try out the formulas, if I try to work out the formulas and I get the answers that I'm supposed to get, then I can say I understand it.
Okay, you're being cautious, not to not to be overambitious, but that's fine. I agree. I completely understand where you're coming from. But I hope that's clear, because it's foundational to some of the things that we'll be doing going forward.
Prof, for me, I can say it's understandable. We just need to know the formulas. And I believe that formulas will not be provided in assessments.
No, for this one, I think we can provide the formulas,
It will be.
especially for B, but yeah, it's
Oh,
good
okay.
to
So,
know the formulas, but I think it's fine for this, we can provide the formulas. In any case, except maybe the exam, the test will be online, so it would, technically, I will not be there to see whether you're looking at the formulas or not, so yeah, but by the exam, it will be good that you know them. I don't know whether it will be physical or not. And that reminds me, I've uploaded the videos for the last lecture. I don't know whether anybody tried to download it.
on YouTube, sir.
Yes, on YouTube. I think the link is still open, so it's not private, it's public, so you should be able to access it if you have the same link. Vita, were you finally able to access the previous video, the one before last class?
Yes, Prof, I was.
On YouTube?
On YouTube, yes.
Okay, that's fine then. Okay, so we have about 45 minutes left.